Okay, so it's a pleasure to welcome our next speaker, Silvestre from University of Chicago, who's going to speak on fully nonlinear integro-differential equations.
All right, thank you, and thank you for the organizers, to the organizer for the invitation. So I think the title in the schedule was different to this. I forgot what title I gave, and the title in the schedule is a bit better than this one because it's more specific. I'm gonna talk about regularity results for nonlocal equations. And so what we do is a joint work with Luis. What we do is we reproduce the regularity theory for fully nonlinear elliptic PDEs in a nonlocal setting. So more specifically, the results that we want to reproduce are the Kirchhoff-Harnack inequality and the Evans-Kirchhoff theorem for nonlocal equations. So first of all, I want to show what type of nonlocal equations we can deal with. And these are the equations. I'm going to motivate them using probability. Fully nonlinear elliptic PDEs can be obtained by stochastic control problems with diffusions. If instead of diffusions you take discontinuous Levy processes, you end up with integro-differential equations. And if you take control problems with those equations, you get nonlinear equations. And those are the equations that we have in mind that we want to be able to deal with, even though the theory may be more general than that because the assumptions that we take may apply to other equations too. Those are the natural applications. So I'm going to start with a motivation for the equations. So let me remind you quickly how second-order PDEs appear from probability. So how is the Laplace equation? How does the Laplace equation come? The Laplace equation is related to the Brownian motion. If we have a function g defined on the boundary of a set, and we take a Brownian motion starting at a point, this is a beautiful picture of a Brownian motion, and we wait until it hits the boundary, and then we take the expectation of the function g at the first point the Brownian motion hits the boundary, and that's going to be a function of the point that the process starts. And that function is exactly the solution of the Dirichlet problem for the Laplace equation. Laplace of e equals 0 in the interior and u equal g on the boundary. If instead of Brownian motion we take another diffusion, we're going to get an equation with coefficients. So this picture intends to be a diffusion that likes to move in the horizontal direction better than in the vertical direction. I don't know if it can be appreciated, but that's what that is. So if you get an equation for a diffusion that likes to move in the horizontal direction better than in the vertical direction, you will end up with an equation that is a large number times uxx plus uyy. So you end up with an elliptic equation with coefficients. And those coefficients could depend on the point. Maybe in some points the diffusion likes to go in one direction more than another, and at another point it's a different preference. So you have different coefficients here. But those coefficients are always a positive matrix. So these are always linear elliptic equations. What we could do is consider control problems. Let's say that we have at every point, according to we have some control on the diffusion, we have some choice, and we can make the diffusion have a preference to go in one direction or in another. So if we wanted to minimize the expected value of the function g the first time the diffusion hits the boundary, we will end up with, so at every point x we have the choice from a family of matrices of what coefficients we want to put at that point. And the solution of this infimum is going to be the solution of an equation that is an infimum of linear equations. And once you take an infimum of linear equations, that's already a fully nonlinear equation because it's nonlinear in the second order part. So in fact, this is any f of d squared of u for an elliptic concave f can be reproduced this way because it's just an infimum of linear functions, right? So the type of equation that you reproduce in this way, the Hamilton-Jacobi-Bellman equation, that is the infimum of linear one, is actually a fairly general family. And there is an important theorem of Evans and Krylov that says that the solutions of this equation, if the coefficients are uniformly elliptic, are C2 alpha. So it always has classical solutions. We could also consider a control problem. Let's say there are two opponents. One wants to minimize the expected value on the boundary. Let's say I have a control alpha, and I want G to be as small as possible. But then Diego is there, and he wants it to be as large as possible, so he has the other control beta, right? And we are going to be competing, right? And so the optimal strategy for Diego and I for the expected value for G and the endpoint is going to end up being a solution of an equation that is the subinf of linear. And with subinf of linear, you pretty much recover any fully nonlinear elliptic PDE, because if you take fully subinf of linear, you can reproduce any function. So the fact that you only take positive matrices is what tells you that the equation at the end is elliptic, and that's all you can get. Kirchhoff-Safonov theory tells you that if, at least in the uniformly elliptic case, the solution of these equations are C1 alpha for some positive alpha. In this case, you cannot prove the solutions are classical. This is not enough to get C2 regularity. So this is a fairly general. What I'm saying is that with these stochastic control problems, you can reproduce a fairly general set of equations. Even though with all these equations were motivated with probability, it applies to more things than only probability. So to give you an example, you can write Monchampère as a Hamilton-Jacobi-Bellman equation, right? This is how you would write that. So how is it that we get nonlocal equations? Nonlocal equations come if instead of diffusions, we take jump processes, discontinuous processes. That should be the bar in the other direction. So this picture that is much uglier than the Brownian motion is a Levy process, a jump Levy process. So it starts at one point, I start jumping around. These lines are actually discontinuities of the process. It's called jumping from one point to another. And we can take starting at the point x, we can follow the process until it leaves the domain. And once it leaves the domain, we take the value of a function g. We compute the expected value at of g of the first point it exits the domain. And that's going to be a function depending on the initial point. And that function is going to satisfy an equation, but this time it's not a differential equation, it's an integro-differential equation. So what this equation is an average of differences of u of xy, like u at any other point, with the difference with respect to ux. And so it's like a non-infinitesimal differential equation, because you are averaging differences, different quotients that are far away. So what are the kernels that one can get with this type of equations? The kernels are always going to be positive functions, because they represent the frequency of jumps in every direction of the process. And they have to be, the integral has to be well defined when u is C2. So I'm going to take only symmetric kernels to make it simpler. So if the kernel is symmetric, to have this integral defined at least in the principal value sense, I'm going to need it to be close to the origin. It has to integrate against the quadratic function, because if it's symmetric, the linear part is going to cancel out. And the tails have to be integrable, so that if u is bounded on C2, that's well defined. What's the most typical case? The simplest case that I would have in mind is the fractional Laplacian. Fractional Laplacian is the one that has a kernel that is 1 over y to the n plus sigma. So it's a kernel that is radially symmetric and homogeneous. And so this is the operator that plays in in second order equation, it plays the role that the Laplacian plays in second order equation. It's the one for which all the regularity estimates come easily, and for which you define ellipticity to be for an operator when the operator resembles the behavior of the fractional Laplacian. So it's called fractional Laplacian because in Fourier it's actually the fractional Laplacian as a positive operator. So it's a pseudo differential operator has symbol xi to the sigma. So if sigma is 2, you get exactly the Laplacian. And so we want to define ellipticity. Our ellipticity is going to be that we want to study integral differential equations that behave more or less similar to the fractional Laplacian. So for a linear if you have a linear operator, this is going to be a uniformly elliptic of order sigma if it's symmetric and if the kernel is comparable to the kernel of the fractional Laplacian from below and above, right? And in the same way we were doing for diffusions, that we had the control problems, we can also do control problems for Cham processes. So we can take the supremum of a family if we want to maximize the expected value when the process exits the domain. We could take the infimum, we can take the inf sup if I'm competing with Diego, or we can that's a way to get nonlinear problems that are integral differential. So these are the problems that we would like to have a theory that gives us regularity results for this type of equations, right? And it's important to point out that the second order equations are limit cases of the integral differential equations. And the integral differential equations are a very rich class because you can choose different kernels, you can have a lot of different integral differential equations, and you can recover the second order equations as limit cases. And usually you can recover them as limit cases of very different families of integral differential equations. So you have several different ways to get the second order PDEs as limits. Here we have 2 examples on how to get the Laplace operator as a limit of integral differential. When one studies the Dirichlet problem for a nonlocal equation, then the natural problem would be like this. We have the equation inside the domain, and the boundary condition is actually given in the whole complement, not only on the boundary of the set. That's because the operator is nonlocal. So the value at a point depends on the value of the function in the whole space. If I knew only the value of the function inside the domain, I wouldn't be able to compute the operator, and I wouldn't be able to say what the solution is. From the point of view of the stochastic processes, it corresponds to the fact that when the process jumps outside the domain, it can jump anywhere. It's not going to stay on the boundary. And for this type of problem, it can be proved that the problem has a unique viscosity, a unique solution in the viscosity sense. So I don't want to talk too much about existence and uniqueness today, but the theory for existence and uniqueness is not too different to the theory of existence and uniqueness of viscosity solutions for fully nonlinear second order PDEs. So viscosity solution is a way to define what a weak solution is in this context, and has to do with the fact that it has to satisfy comparison principle, because all these equations satisfy comparison principle. That's something it has in common with elliptic equations. So I want to talk about regularity of these equations. So let's review what the regularity results are for second order elliptic PDEs. So the regularity has to do with the concept of uniform ellipticity. Let's see what uniform ellipticity is for a second order PDE. If we have f of d squared of u equal to 0, this equation is going to be uniformly elliptic when f satisfies the following thing. If we take any matrix x and a positive matrix y, and we compute this difference, f of x plus y minus f of x, this is going to be bounded below and above by a multiple of the norm of y. This is when y is a positive definite matrix. This is the definition of uniform ellipticity. that if f is a smooth function, it would be equivalent to say that the derivative of f is bounded below and above. This is the first derivative, right? F depends on matrices. That's why it has two subindices. So this is the definition of ellipticity, of uniform ellipticity with constants small lambda and lambda. And it's useful to understand what the extremal operators with the uniform ellipticity property are. So those are the Pucci extremal operators. So these are the operators that, let's say if you say f of 0 equal to 0, this would be the maximal operator with given ellipticity constant and the minimum one. So and they have a short formula. The maximal Pucci operator would be the small ellipticity constant times the sum of all the positive eigenvalues plus this big constant times all the I decided the other way. So it's like if I want to get the number as large as possible, I have to take all the negative eigenvalues and multiply it to the constant as small as I can, and that's the small lambda of the ellipticity. And the sum of all the positive eigenvalues has to be multiplied times the largest possible constant, and that's the big constant lambda. And the minimum Pucci operator is the opposite choice. The ellipticity of the equation can be rewritten in terms of the maximal Pucci operators, that the difference is bounded above and below by the maximal Pucci operator in y and the minimal Pucci operator in y. And this has a slight advantage that now I don't have to require y to be positive definite. This is for any two matrices x and y. So what are the results for fully nonlinear second order PDEs? These are the results that we want to reproduce in the non-local setting. So first result is the Kirchhoff-Harnack inequality that implies Helder estimates that says if u is a bounded function in B1 for which the maximal Pucci operator is positive and the minimal Pucci operator is negative, then u is Helder continuous in a smaller ball. You see that this assumption is actually very weak because m plus is the largest of all uniformly elliptic operators, right? And m minus is the minimum one. So if we have an equation equal to 0, uniformly elliptic equation equal to 0, it's always going to be in between those two. That's even if it depends on x, even if it's whatever. So if the way people understand this usually is say if you have a linear PDE aij x dij u equals 0, and you know that aij may be discontinuous, but it's uniformly elliptic, then having an equation like this would imply that u is in between those two. So people usually say for aij just measurable. I think the word measurable is used just to scare people, to stress that you are not requiring aij to have any continuity, right? And I'm not even sure measurability is required. So this is what I mean is that these conditions are very, very general. And the way this is used is if you have a uniformly elliptic equation, f of d squared u equal to 0, when you apply the derivatives to this equation, you differentiate the equation. Maybe I can do that. If you have an equation like this and you want to prove that it's C1 alpha, you would take derivatives of the equation. If I take derivative of this equation with respect to one direction E, I would get derivative of f with respect to xij at d squared u times dij ue equals 0. So this is a coefficient that I don't know anything about its continuity because it depends on this square of u, and this square of u is whatever, I don't know. But all we know is that this as a coefficient is bounded below and above. That was the ellipticity, uniform ellipticity condition. So this says that the derivatives of the equation satisfy an equation like that. So that's the idea of how you would prove that that a solution of a fully nonlinear PDE has Helder continuous derivatives using the first result. And then the third regularity result for fully nonlinear PDEs is the Evans-Krylov theorem that says that if our fully nonlinear equation is convex or concave, so that adds some extra condition, then the solutions are actually C2 alpha. So in this case, this is the one I mentioned before. The solutions are classical. So these three results are the results that we reproduce in the non-local case. So you see that we have to make sense of being elliptic for a fully nonlinear integro-differential equation. And I want to have it's good to have a fairly general definition of ellipticity, as general as possible. So this is a small observation I'd like to make, that imagine if you take any operator, whatever it is, non-local, and you check this condition that if you apply it to a function and then you apply it to the sum of two functions and you subtract, then the difference is bounded above and below by the usual extremal Pucci operators applied to v, the one with the difference. So then this is forcing the operator to be a second order differential operator that is uniformly elliptic. So not only is forcing uniform ellipticity, it's forcing the operator to be differential because it forces it to be local. Because if, let's say, if you have two functions that coincide in the neighborhood of a point, then that function v would be 0 in the neighborhood of a point, and you get 0 and 0, and these two things are the same. So it's forcing the operator to be local. So this was the definition of uniform ellipticity for second order PDEs. What we want is a definition of uniform ellipticity that uses a different family, a different pair of extremal operators. So if the extremal operators for second order equations are the supremum of all possible choices of linear uniformly elliptic operators, what we want is to have an extremal operator of order sigma to be the supremum of all interdifferential operators of order sigma that are uniformly elliptic. So for the Pucci operators, there was a pretty formula, short formula, to compute that. For this one, there is also a short formula because we are taking only symmetric kernels. So here we can average the value at y with the value at negative y. And then we see that whenever the second order incremental quotient is positive, we are going to want to put the maximum possible coefficient in front of it. And whenever it's negative, we want to put the smallest possible coefficient there. So the maximal operator of order sigma would be integrating all the positive second order incremental quotient times the big lambda and all the negative second order incremental quotient times the small lambda. And then use the kernel of fractional Laplacian. So we can state the condition of uniform ellipticity for non-local equations as that if we take the difference of the operator applied to two functions, that's controlled by below and above by the extremal operators of order sigma applied to the difference. And this is really the only condition that we need to develop our theory. There are some extra technical conditions in the proof that I'm not going to mention, but anyway. But this is a condition that we need to get our regularity results, and it's also the conditions that you need to do the existence and uniqueness result. So the operators that I wrote before, the linear operators that are uniformly elliptic and the im sup, or the supremum of linear operators, they all satisfy that condition, right? But maybe you can come up with some other operator, let's say some fancy integral like this or something, that also satisfies that condition, and then the theory will apply. So it's the theory that this is a condition that includes the cases of optimal control for Cham processes. That was our initial motivation. So what are the theorems that we can get? So if this could be the non-local version of Kirchhoff-Saffonov-Harnack inequality. If u is a function that is non-negative in the whole space, and the minimal operator is non-positive, the maximal operator is non-negative, then the supremum is controlled by the inf in a smaller ball, smaller with respect to where the equation is satisfied. So here there is a small difference with respect to the usual Harnack inequality. That is that the non-negativity of u has to be in the whole space. That's because the equation is non-local, so things that happen far away can affect the equation. If u was negative at some points very, very far, if you have some control on how negative it is, you can put it into the equation and work it out. But if you have no control, then it's hard to deal with that. There are a few things that are worth mentioning. First, the constant that we get there does not blow up as the order of the equation goes to 2. So we can recover Kirchhoff-Saffonov-Harnack inequality from this. I would say the proof also becomes the proof of Kirchhoff-Saffonov-Harnack inequality. So it doesn't really add, at least in this theorem, anything new to the second order case. But it makes the theory of non-local equations and the theory of second order PDEs somewhat unified. And in the same way that for the Kirchhoff-Saffonov-Harnack inequality, being in between two Puccis could be understood as being a solution of an equation like that with measurable coefficients, then the condition of being in between two of the extremal operators can be understood as being a solution of a linear equation with a kernel that depends on x. And the dependence on x can be disastrously discontinuous, right? As long as it stays uniformly elliptic for every x.
So it's important to put a 2 minus sigma there in the definition.
The 2 minus sigma here has the purpose to pass to the limit as sigma goes to 2. So we want the estimates to not to blow up as sigma goes to 2, and we want the equations to become second order equations as sigma goes to 2. This is a normalization factor. So when you have the fractional Laplacian, you have a constant in front that depends on the order and the dimension. The constant is like 2 minus sigma for sigma close to 2. And for sigma close to 0, the constant is not like that. And we don't get anything for order equal to 0, right? Because it will be u equals nothing. So, but it's important that we can pass to the limit. That's why we have that that constant over there. Okay. So I was saying that we also get Helder estimates, not only Harnack inequality, but also Helder estimates. In the local case, it's very trivial that the Harnack inequality implies Helder estimates. That's a well-known fact. In the non-local case, you have to work a little bit because you have to compensate the errors from outside, from the fact that we were asking the function to be non-negative everywhere and not only in the same domain as the equation. But that's not really too complicated. So with the same conditions as in the previous one, we get that the solutions are Helder continuous. So applying the same trick as here, the previous result allows us to prove that the solutions of an arbitrary nonlinear elliptic operator is going to be are always going to be C1 alpha for some positive alpha. So this nonlocal operator, the only thing it has to satisfy is that it has to be uniformly elliptic, in the sense that if we take the difference of, if we apply to two functions and we take the difference, that's controlled by below and above by the extremal operators. And again, the constant does not blow up as sigma goes to 2, because the previous constant in the Harnack inequality didn't either. This is the operator applied to the constant function 0, in case you're wondering. Just ignore it. And we can also reproduce Krylov-Safonov theorem in the non-local setting. So for second order equations, Evans-Krylov theorem says that if you have a uniformly elliptic equation that is convex, then the solutions are C2 alpha. 2 is the order of the equation. Here what we get is that the solutions are C sigma plus alpha when sigma is the order of the equation. So we get a bit more regular than the order of the equation. And that's enough. When we write the equation as an inf soup of integro-differential equations, that's enough to say that the solution is classical, because this is enough regularity so that all the integrals are well defined and Helder continuous. All right, so these are the results that we can prove. I would like to say some ideas on the proofs. So if you see the proof of, well, I should say something else about this. I said that the proof of Krylov-Safonov Harnack inequality for the non-local case, if we take sigma go to 2, it pretty much becomes the proof of the second order case. For the Evans-Krylov theorem, it's not quite the case. There are some differences with the proof that we get and the proof for the second order case if we follow the proof and we follow all the ideas that are used. If I have time, I'm going to explain it at the end, but I don't know if I'm going to have time. So the proof of Krylov-Safonov Harnack inequality, well, I don't know if you know it, but it's a long proof. But it uses very strongly the Alexandroff-Bakelman-Pucci estimate. That's at the heart of the proof. It's really the main tool for the proof. So what I'm going to explain is how the Alexandroff-Bakelman-Pucci estimate looks in the non-local setting. That's what I want to explain, because so let me review what the Alexandroff-Bakelman-Pucci estimate is. The Alexandroff-Bakelman-Pucci estimate is a way to compare the maximum of a function that is a subsolution of that equation with the ln norm of the right-hand side, but only computed at the points where u coincides with its concave envelope. And the way this estimate is used in the proof of the Krylov-Safonov Harnack inequalities is interesting, because you could think that this is not very important, and this is a way to compare the ln norm of the right-hand side with the maximum of u. But actually, it's very important that it's only on the contact points, because in the proof of the Krylov-Safonov Harnack inequality, this is used to estimate the measure of that set. Because it's a way to pass from estimating measure to a pointwise estimate. It's a way to say that if you have a function, its solution of the equation, let's say an equation equal to 0, then you subtract the test function, you end up with an equation like that, and you end up comparing the maximum the value of a function of u at one point with the measure of the points where u is very large. That's the way you end up using that. So the important thing of this estimate is to use it to estimate the measure of that set, of that contact set. And the proof of the Alexandroff-Bakelman-Pucci estimate is actually is very nice. And I would say this line is the whole proof. So I'm going to explain it. So look at the maximum of u would be like this point over here, right? And if you know the maximum of u in B1, you take its concave envelope. U is a function that is negative on the boundary of a ball. When I take the concave envelope in a slightly larger ball, I know that the concave envelope is going to contain, if I look at all the supporting planes and all the gradients of all the supporting planes of the concave envelope, that's going to contain a ball whose radius is comparable to the max of u. Why is that? Imagine I take a plane that the slope is not very steep, right? And not very steep is something proportional to the maximum. So if I slide that plane from above, I'm going to touch that point before touching the boundary of this ball. So that means that I'm going to touch the graph of the function before touching the boundary. And that's exactly what the meaning of this. That exactly means that supporting plane, that slope is a slope of some supporting plane of the concave envelope. So the image of the gradients of the concave envelope contains a ball whose radius is comparable to the maximum of u. And that's why we have this inequality. All right? Then this equality over here is just integrating the Jacobian of the transformation gradient of gamma. And the fact that I'm integrating only on the contact set is because every supporting plane is a supporting plane at some point on the contact set. And now, why is this last inequality true? That's because on the points that the function coincides with the concave envelope, the Hessian has a sign. Here I have the product of the eigenvalues. Here I have an average of the eigenvalues, a weighted average. And there is always an inequality that the weighted average, if you have n positive numbers, the average is always larger than the nth root of the product, right? That's the arithmetic mean and geometric mean. And if you put the constant in front, you can do it with the weighted average too. So that's why we have this last inequality. So that would be like the whole proof of Alexandrov-Bakelman-Pucci estimate, at least if we assume that the functions are smooth enough. What happens for integro-differential equations? For integro-differential equations, well, this inequality doesn't depend on the equation. That equality doesn't depend on the equation either, but it seems that I wouldn't want to use anything depending on the Hessian if I want to do integro-differential equations, because I'm not going to be able to control the Hessian. So let's stop there, and let's try to estimate this with respect to right-hand side of an integro-differential equation, and see what happens if instead of, let's say, instead of the maximal Pucci operator here, I want to do it with the extremal operator of order sigma. So what's the point? Let's suppose that the extremal operator of order sigma is greater than negative f. So my extremal operator of order sigma has that form. I want to see what I can say. The point is, if I evaluate this at the point on the contact set, I have a plane that is completely above the function. That means that all the second order incremental quotients have the same sign. They are all going to be negative because I'm below the tangent plane. So there is no cancellation in this integral. I only have the second term. And there is no cancellation. If there is no cancellation, I can compare this with the function of y that would give me a larger value. I mean, let's forget about these negative signs. I know that this integral has to be less than f. If I compare this integral with the integral of a y squared, let's say, for a large constant a, this integral has to be less than that. So that's still going to tell me that this function is going to be less than that in many points in measure. And so let's take a ball BR. We can estimate how much that is. So what I put in the right-hand side is actually f of x, because the integral of that is a times some constant. And we can take BR and split it into dyadic balls and add up all those dyadic balls, dyadic rings, sorry. Split into dyadic rings. So there's going to be one ring where this inequality still holds. And that means that in that ring, this thing cannot be larger than that one in a large proportion of the ring. So we end up saying, well, instead of using the second incremental quotient, I'm using the difference of u with the supporting plane. So the difference of u with the supporting plane cannot be less than ay squared in a large portion of the ring. And that's what I wrote in this lemma, the same thing. There is some radius r for which the function does not separate from the tangent plane at many points. And there is a quantitative estimate on how much that is. So if a is an arbitrary number, take a large number. If a is very large, that's going to mean that the function doesn't separate from the tangent plane in most of the points in the ring. If we look at the concave envelope is always above u. So the concave envelope doesn't separate from the tangent plane in most of the points in the ring. And since the concave envelope is concave, when we go inside, the concave envelope doesn't separate from the tangent plane in any point because it's concave. Like the fact that it stays closed for most of the points is going to make it stay closed for all the points inside. So the concave envelope stays close to the tangent plane for all the y's in the little ball inside. And so we can cover the whole contact set with balls with that satisfy that property. Balls that u stays close to the concave envelope, let's say, in a large proportion of the ball. And since the concave envelope was separating from the ball at the ratio of r squared, that was how much it would separate, then the gradient it's only proportional to r. It's containing a ball of radius r in there, so it's going to be the image of the gradient map in that ball is going to be proportional to the measure of the ball. So we can cover the whole contact set with these little balls, and we would find out that the image of the gradient map in the whole domain is controlled by the measure of the set where u does not separate too much from the concave envelope, right? Because this measure comes from that happens in a large proportion of every ball, and in every ball the measure of the ball is comparable to the measure of the image of the gradient map. This R0 is the maximum radius that you have to take so that the computation actually works. And it's funny that the R0 goes to 0 as sigma goes to 2. And so the smaller R0, the better. But anyway, the important thing is that for some R0, it works. So we finished the chain of inequalities by saying that the c times the maximum of u is controlled by the measure of the set where u does not get too far from the concave envelope. And this is not the same as the estimate we had in the Alexandrov-Bakelman-Pucci estimate, but it's enough to do the proof of the Kirillov-Safonov-Harnack inequality. In the Kirillov-Safonov-Harnack inequality, this was used to make relate a point estimate with a measure estimate, and this is what this is, and it's enough to carry out the rest of the proof. I'm not going to do the rest of the proof because it's long, but if you know the proof, or if you have ever seen the proof, you may remember that something like this is used. So this is our substitute for the Alexandrov-Bakelman-Pucci. in the integro-differentiable case. So what happened? Oh. So if we have a, so I'm gonna, that's what as much as I'm gonna say for the Harnack inequality and Helder estimates. I'm gonna make a few other comments about the proofs. I don't know if I'm gonna be able to prove Evans Krylov, probably not, but I'm gonna make a few other comments. So if you take two solutions of the same equation and you take the difference, then that difference is going to be the maximal Pucci operator positive and the minimal Pucci operator negative. That's because of the definition of ellipticity of the operators. And like I said, this can be understood as that u minus v satisfies an equation with discontinuous coefficients, with some kernel that depends on x, and the dependence in x can be arbitrarily discontinuous. So another way to understand this is that the positive and the negative part of this integral, one controls each other. Because saying that there is one kernel that is controlled by below and above that makes the integral 0 is like saying the positive and the negative parts are comparable. So this is just notation I use for the second order incremental quotient, so that the integrals don't look so big. But by this, I just mean that second order incremental quotient. So in particular, we can apply the previous idea to incremental quotient of the solution. So I said that the difference of solutions satisfies an equation. Well, one possibility, one example of a difference of solution is an incremental quotient. So if we apply the previous result to an incremental quotient, we get that the incremental quotient satisfies that equation, and that implies that the incremental quotients are C alpha. And that's how we get the C1 alpha regularity of solutions. It's pretty much the same scheme as I was explaining for the second order case. So there is a little bit of a difficulty because let's say you already know that U is Lipschitz. You take this incremental quotient that's going to be bounded inside the domain. Outside the domain, I don't know, because outside the domain I have the Dirichlet data. That could be a disaster. So you have to compensate for the errors from outside. And so there are some technical difficulties there that you have to compensate. But I don't want to. That's mostly technical, just estimating the errors of the tail of the integrals. If we have an operator that is a concave operator, what happens is that the average of solutions is a subsolution. That comes from the definition of concave. If you have an operator, an operator is equal to 0 for many functions, then we take the average of the functions to be larger or equal than 0. So in particular, if you take a second order incremental quotient, you have a subsolution and a solution. You take the difference and you get a subsolution of the maximal operator. So this is something that happens for the second order concave equations in the same way. The same story can be done if if you take an integral differential operator and you apply it to a solution, it's going to end up being a subsolution of the extremal operator. Why is that? Imagine if k was L1. K is never L1 in any of our cases, but imagine it was a positive L1 function. So this thing over here would be the convolution of u with k minus the integral of k times u. So this would be a subsolution of the equation because it's an average of translates of u. This would be a solution. You subtract, we get the subsolution. So I cannot say this I cannot make this equality for k, but because this k is not in L1, but then you can truncate the tip and approximate, and you get that. So the linear operators would be subsolutions of the equation. if you look at the proof of Evans-Krylov theorem for the second order equations, it's clear. It's also they use that the second order incremental quotients are subsolutions of the equations, but that's not enough to make the proof. You also have to use the equation a little more to say that the positive part of the Hessian is controlled by the negative part. That's what I was mentioning before when I said that the positive part of the integral controls the negative part of the integral. That would be the corresponding thing in the non-local case. You have to use a little bit more. You have to use that if you take the difference of two solutions, then the difference, if you take the Hessian if you take the Hessian as 2 points, you take the difference, the positive part, and the negative part have more or less the same size. These are the two main ingredients that are used in the proof of Evans-Krylov in the second order case. So in the integro-differential equations, we also have that the positive and the negative part of that equation control each other. So now you see the purpose of having the notation for the second order incremental quotient, because otherwise I would have to have the formula up to here. So the positive and negative part of the integral control each other, and also the so if you take the positive part of this is a subsolution of the equation because it's a supremum of all the. If it didn't have the plus, it would be a super solution. If it has the plus, it's like taking a supremum of all k's multiplies times some characteristic function of a set. In any case, you can ignore the plus over here and say that this is a subsolution of the equation. So these would be the two main ingredients that would be used in the proof of the integro-differential Evans-Krylov theorem, and they correspond to the proofs to the tools that were used in the second order case. So the proof will have like 2 steps. The first one to prove that the integrals all converge absolutely, and this is like in the second order case to proving that solution are C11. I would say that the proof of this step follows more or less the same ideas as the proof of Evans-Krylov in the second order case. Then there is a second step where you prove a little more regularity, that the regularity of the solution is more than the order of the equation. That would be, in the second order case, proving that once you know that the solution is C11, the solution is C2 alpha. The proof of this is a little bit different than the proof in the second order case. But predictably, I don't have enough time to explain it, so I'm going to stop here.